Good morning. I am E. Ilavenil, and today we are going to see about an important topic in engineering mechanics: equilibrium of rigid bodies. A rigid body is a solid which does not undergo any deformation. So it is said to be a rigid body where the original dimensions are preserved. Though all solids deform under external forces, they are treated as rigid bodies for the purpose of analysis. Most solids undergo little deformations, and the rigid body idealization does not affect the equilibrium condition. Rigid body versus a particle. A rigid body is made up of a number of particles. The shape and size of the body is not the essential feature which distinguishes a rigid body from a particle. For equilibrium analysis, a body is treated as a particle if all the forces are concurrent. That is, when all the forces pass through a single point, it is concurrency, and with the condition of concurrency, we consider a body to be a particle, or else it is considered a rigid body. Example 1. A planet, which is a huge body, is treated as a particle because we consider the forces acting through its center of gravity. Whereas a lever in a lock is treated as a rigid body because the lever, where different forces act at different places, makes it a rigid body. So here we have some examples of rigid bodies. So here we have a circular object which is going to rotate and slide down. Since it contains a rotation as well as movement, the rotation corresponds to rigid bodies rather than particles. In a particle, the entire mass is considered to be concentrated at a single point where we cannot consider any rotation. Here there is some rotation indicated here, which means this is a rigid body. So here we have a beam which is supported in a sharp knife edge, and we have a few forces acting upon. So we clearly see that these forces available here are not concurrent. They act at different points, and here also we are going to have a reaction from this knife edge. So these forces are not concurrent, and this body is to be treated as a rigid body. So here again we have another body where we have one force here, another force here, and another force here, and it is very obvious that these three forces are not concurrent. So again this can be considered as a rigid body. So as told earlier, all these three bodies can be originally deformable, whereas their deformations are neglected and they are considered rigid. So next we are going to see about the conditions of equilibrium. So the first condition, sigma f is equal to 0, that is in vector form I sigma fx plus j sigma fy plus k sigma fz is equal to 0. So here I, j and k are unit vectors in the directions of three axes x, y and z. So this is also known as the condition of equilibrium of particles, and it holds good for rigid bodies also. But for particles, these are the conditions, that is, this is the only condition applicable to particles, whereas for rigid bodies this should be followed along with another condition, that is sigma m is equal to 0, which can also be written as I into mx plus j my plus k mz is equal to 0. Concept of free body. All the forces acting on the body should be taken into consideration. So here we include all the externally applied forces and the forces exerted by the connecting bodies inclusive of supports. So all these forces are represented as a free body by removing all the connections and in their place indicating the corresponding forces exerted. So here we have some examples of free body diagrams. So this is the original or the real arrangement, as we say. So here we have a knife edge, and this is a beam which is supported by a string, and it contains a load over here. So at this knife edge support we may have a reaction which contains two components of force, one horizontal component and a vertical component. So that is available here, and then corresponding to the load we have a vertical force being represented here, and at the position of the string we remove the string and we represent it with a tension force which is to be acting upwards on the beam. So this total beam removing the supports, loads, etc. and representing them with the corresponding forces makes it a free body diagram. Here again we have one more example. We have a beam here with a knife support and with a load, and here we have a roller support, and here the beam is also supported by a cable. So corresponding to the cable available there, we have a tension which is represented as a force here, and we also have a reaction available here, and here we have an inclined force, of course, which can also be represented with a vertical and horizontal component, but here it is represented as a single force at some angle. So here the load is represented by a vertical force, and here the roller support provides a vertical reaction. So all these put together, where all these supports, load and the cable, all these things are removed and the corresponding forces are represented, and here again we have a free body diagram. The purpose of the free body diagram is to conveniently represent all the known and unknown forces to easily apply the equilibrium equations, and thus we solve for the unknown forces. A support restrains one or more degree of freedom by exerting a reaction. So supports are classified by the nature of restraint provided by them. Here we have a number of different types of supports. So this is a roller support. So here when there is a roller which can roll along the horizontal direction, we have a vertical reaction. So here we have an inclined roller. So whenever we have a roller, we have a reaction perpendicular to the direction of movement of the roller. So here we have a knife edge. So there we have an inclined reaction which can be represented through a horizontal and a vertical component. So here we have a hinge or a pin. So again here the same type of reaction with same type of components which are represented here. This is a fixed or built-in support. So here we have similar to this reaction in some direction with horizontal and vertical forces or components, along with a moment which can also be found there. So types of connections and conditions. So first one, taut. So that is without any force, tensile or compressive force. Next one is snug. So it is contact without any gap and also without exerting any force. So whenever we say light, that is a rod or a bar is light, means we can neglect that weight, or else we have to consider that to be a distributed load. And then resting on a smooth surface, which means we neglect the friction, so the reaction is normal to the surface. Then resting on rough surface, we include friction. So cable, rope or string, which means elements can carry only tension. Passing over a smooth pulley means cable is same on both sides of the pulley, that is there is no pulley friction. So the equilibrium condition that is provided 3 equations for 2D statics and 6 equations for 3D statics. So on the isolated free body, the number of unknown forces are to be less than or equal to the number of equilibrium equations. Then only we can solve it. A complex force system can be analyzed by proper free body diagram. So in the next video, we will see that with an example how we go for solving problems with equilibrium equations. So with this, we stop here. So we have seen about what is rigid body, what is a particle, so what is equilibrium, what is support, what are different types of supports, and finally we are getting into how we solve an equilibrium equation.